1.
Modern data processing systems like these use thousands of magnetic cores. These cores are small, rugged, and they consume less power than most of the other devices that are used in these systems. You'll also find magnetic cores in automatic equipment employed for communication, fire control, cryptography, and high-speed computation. What are magnetic cores? They are tiny rings of nickel alloy or other magnetic materials. They have replaced vacuum tubes for many important functions in data processing systems. Cores come in a variety of sizes and in two basic types. The ferrite type of core is molded from compounds that magnetize easily and is used to provide data processing systems with their memories. The metallic ribbon type consists of a non-magnetic spool wound with a thin ribbon of highly magnetic alloy. This type is used in operating circuits of ADP systems. Both types of magnetic cores are remarkably adaptable to the language of data processing. Many ADP systems use the binary system of numbering, which employs just two digits, 0 and 1. These two digits are called binary digits, or bits for short. A bit is either a 0 or a 1, nothing else. Why do we use binary? Because a bit can be represented by any bistable device, and a magnetic core is a bistable device. Bistable, because it can be magnetized in two directions. When the magnetic lines of force point in one direction around the core, they are a positive magnetic flux, and the core is said to hold a binary 1. If the direction of magnetism is reversed, the flux becomes negative, and the core holds a binary 0. However, remember that this arbitrary definition of positive magnetic flux representing binary 1 and negative magnetic flux representing binary 0 may be reversed in some systems. So far, we've been establishing the function of magnetic cores. They store binary digits, or bits, 0 or 1. Now we're going to see how they do it, and also how they transfer bits from one core to another. To explain how cores store binary digits, we must know how they are constructed. Around the core is wrapped a conductor. Current flowing through the winding produces a magnetic field around the conductor. Because the core is made of highly permeable material, it forms a path for the magnetic lines of force. Because it is ring-shaped, the path it forms is a closed loop. The conductor here is wound so that current flowing in this direction produces a positive flux, setting the core in the binary 1 state. Current flowing in the opposite direction produces a negative flux, which sets the core in the binary 0 state. To show the polarity of the winding in a core diagram, we mark one side with a black dot. By definition, current that flows into the winding from the dot side sets the core to 0. Current flowing into the non-dot side sets the core to binary 1. Remember, non-dot current for 1 and dot current for 0. Any winding around the core obeys the laws of electromagnetism. The magnetizing force it exerts is proportional to the amount of current flowing through it, measured in amperes, times the number of turns in the coil. Or, as it is usually expressed, the ampere turns. Since the number of turns in this winding is constant, we can simplify the rule here. The magnetizing force exerted by the winding on the core is proportional to the winding's current. Suppose we increase the amount of current. Will the total magnetism of the core also increase? It will, but not proportionately, as we'll see on this graph. We're going to take a minute and trace the magnetization curve of a core, because in this way we can point out some of the characteristics that make cores so useful. We measure the magnetism of the core in terms of its flux density, which is the number of magnetic lines of force per square inch. The horizontal axis will represent the magnetizing force of the winding. Remember that the magnetizing force is the cause and the flux density is the effect. Initially, a relatively small amount of magnetizing force produces a relatively high flux density. The curve on the graph will begin like this. But as we increase the magnetizing force, the curve flattens out because we are adding proportionately less to the flux density. Further increases in magnetizing force will have no appreciable effect on flux density. The symbol for magnetizing force is the letter H. The symbol for flux density is the letter B. The relationship between magnetizing force and flux density for any given core material is represented by its BH curve. This is the point of saturation. The core is holding just about all the magnetism it can hold. We've been applying a positive magnetizing force here, which produced a positive flux density and brought the core to a state of positive saturation. If we now reduce or stop the magnetizing force, for all practical purposes, there is no change. The core material retains most of its magnetism. Here's how we plot this fact on the graph. The BH curve is brought back to the 0 line on the horizontal scale. Watch the difference in flux density on the vertical scale near the plus B. It's negligible. This, then, is the amount of remaining magnetism. This amount is known as the residual magnetism of the core material. The magnetism that remains after the force that brought it about is removed. When non-dot current sets the core to the binary 1 state, the residual property keeps it that way, indefinitely. Suppose there is a second pulse of non-dot current. It will have no practical effect on the core because the core is already saturated with positive magnetism. But if we send current through the other way, into the dot side of the winding, then, of course, the core's state will change. To plot the effect, we'll extend our graph. With dot current, we're applying a negative magnetizing force represented by minus H. Negative flux density is symbolized by minus B. We need a certain amount of negative magnetizing force to overcome the existing positive residual magnetism in the core. The amount needed is called the coercive force. At this point, the material contains no magnetism. The flux density is 0. Adding more negative magnetizing force produces a negative flux density. And again, the core is brought to a state of saturation, negative saturation. If we reduce or stop the magnetizing force now, there will be little effect on the flux density of the core. The BH curve returns to 0 on the horizontal magnetizing force scale, but it remains at almost the saturation level on the vertical flux density scale. In other words, there is residual magnetism in the negative direction too. Therefore, when dot current is fed into the core, magnetism builds up and the core is set to binary 0. Residual property keeps it there. To switch the core, we apply a positive magnetizing force. Enough first to cancel out the negative residual magnetism. That is, to act as a coercive force in the opposite direction. And then, by adding more positive magnetizing force, we can bring the core material back to a state of positive saturation. We have now plotted the positive and negative magnetization of a core. The original S-shaped curve is produced only when we are first magnetizing the core from a completely unmagnetized state. From then on, we're concerned only with the rectangular loop, which tells us the limits of saturation that can be reached with dot and non-dot current. Also, the amount of magnetism that will remain in the core after the current stops. The word hysteresis comes from a Greek verb meaning to lag behind. A hysteresis loop, therefore, shows how much magnetism remains behind after the force that produced it is gone. The shape of the loop indicates the ability of a particular core material to retain magnetism. Shallow, rounded loop, low residual magnetism. A core of this type obviously requires less force during a switch from one state to the other. Rectangular loop, high residual magnetism, a greater amount of force needed. If a core with a rectangular hysteresis loop is in the binary 0 state, we're going to have to apply a substantial pulse of non-dot current in order to set it to binary 1. A lesser pulse just won't make the switch. Now, how do we get information out of a core? By means of a second winding. Let's follow the transfer of information from input to output. Assume the core is in a state of positive residual magnetism, in the binary 1 state. To change the core to binary 0, we send current into the dot side of the input winding. Dot current switches the core to binary 0, reversing the direction of the magnetic lines of force. If we diagrammed it, we'd see the positive residual field collapse entirely and a negative field build up to saturation. Anytime a magnetic field builds up or collapses across a conductor like this winding, the movement of the lines of force induces a voltage in the winding, and current flows. Observe the direction of current flow, out the top of the winding. The way these two conductors are wound, a pulse of current sent into the bottom of the input winding results in a pulse of current